Yeah?
Well, you're wrong. Work is the energy expended to displace or move an object.
Now you're doing work. Simple machines like ramps aid in the transfer of energy and work done. The ramp did the work for you instead of you having to do the work and move the car. In the equation, W equals F delta X cosine theta. Cosine theta is used because it is the only component being used since the car is on the x-axis on the ramp.
Power is the rate of work being done or the energy expended.
This student is 84 kilograms. If he runs 25 meters in 5.5 seconds, how much power does he exert?
To show this, we use the equation power equals work over time, where work will break down into force times delta x over time. Simply plug in the information you have and then solve, where now the power will equal, with significant figures, 3,700 watts.
There are two kinds of energy.
Potential and kinetic.
Energy is never created or destroyed. Imagine a world in which friction didn't steal energy. Pendulums would never stop until we made them. Welcome to the Physics Zone.
Unfortunately, we live in a friction-filled world.
So that means energy is taken away, like when a ball rolls down a hill.
At the top of the hill, it starts with potential energy and turns into kinetic.
However, friction steals energy too, in the form of work.
That leaves us with an equation like this.
Using this, we can solve for the distance the ball has traveled, the force of friction that took place, or the velocity the ball will have at the bottom of the hill. Work and energy are related, as shown in the work-energy theorem, where negative W is equal to KE, which is kinetic energy, and sorry for that being crooked, which means that when it's negative, work is done on an object and it gains a velocity. W can also equal PE, which is potential energy, which means it takes energy to do work, so it loses energy. However, energy is never gained nor lost, so no matter what energy problem you have, and energy initial is always equal to energy final. To show this, we have a sample problem in which a bow, like in a bow and arrow, is shot straight up with the shooter hoping to hit a target 15 meters above the ground. If the force of the launch is 20 newtons and the bow weighs 0.40 kilograms, will the shooter be able to hit the target when the bow is launched? So, the best thing I would suggest to do is to draw a picture. And since I'm not a good artist, it's going to look okay. 40G, my little target, that's 15 meters above the ground, and it's shot at a force of 20 newtons. Alright, so to solve this problem, its work of the launch of the arrow is equal to potential energy, since the arrow has not been launched. So, it's F of launch times delta Y is equal to mgh. So we have 20 newtons, since that's the force that it was launched at, times delta Y, since that's what we're trying to find, is equal to 0.4 times 9.81 times 50. And you can just divide by 20 on each side to get delta Y by itself. And you have delta Y is equal to 0.4 times 9.81 times 50 times divided by 20, and in total you get delta Y is equal to 9.81, and using sig figs you get delta Y is equal to 10 with 1 decimal point for sig figs meters.